All right, let's jump right in and completely reframe how we think about the artificial intelligence boom. For the longest time, the narrative has been entirely focused on the chips themselves. It's always about who has the most compute or who has the absolute best architecture. But as AI scales up to these just unprecedented levels, the rules of the game are fundamentally changing. We're moving away from a world where silicon is the only limit, and we're entering a world dictated by heavy metal, vast electrical grids, and, well, fundamental physics. So today, in this explainer, we are going to unpack the incredible engineering journey that makes modern AI possible. Everybody assumes the ultimate bottleneck is just getting your hands on the latest NVIDIA GPU, right? But the present reality is actually this massive, heavy civil and electrical engineering challenge. Think about it. In the very recent past, the biggest headache for any tech giant was simply securing high bandwidth memory and those brand new chips. But today, the constraint has totally shifted. The true bottleneck right now is securing gigawatt grid connections and sourcing electrical transformers that have multi-year lead times. You can have literally all the advanced silicon in the world, but without the colossal infrastructure required to power it, it doesn't do a thing. Because it all boils down to this really harsh reality. Without power, those incredibly advanced chips are simply expensive paperweights. Tech companies are pouring billions of dollars into clusters of the most precision-engineered silicon in human history. Yet, we're hitting this fascinating physical limit where they literally cannot plug them in. The absolute bleeding edge of software and microcircuitry is currently being held back by our ability to pour concrete and bend massive amounts of rock copper. Crazy, right? We're actually in the middle of a massive macro shift right now. In the silicon era, everything was all about stacking chips and maximizing density. But today, we're in the power era. We're talking about entire substations, 1.5 gigawatt power capacities, and primary grid flow. It's no longer just a data center anymore. We're talking about an industrial-scale energy processing plant that just so happens to output artificial intelligence. And we've literally hit a wall with physics on our legacy systems. To power a modern AI rack using the old 54-volt architecture, you'd have to push roughly 10,000 amps of current through the cables. That creates massive electrical friction, what engineers call I²R heat loss. It generates so much wasted heat that it would literally require a physically impossible cable thickness. If you don't use those massive cables, you just melt traditional copper wiring. Period. It's an undeniable wall of physics. We simply cannot push any more power through those legacy pipes. So what's the fix? High voltage direct current, specifically an 800-volt DC standard. It's an absolute physical necessity right now to stop wasting electricity. By dramatically upping the voltage to 800 volts, we can essentially divide the required current by 15. It's exactly the same logic they use in electric vehicle fast charging. By minimizing that current, we eliminate the excess heat, we shrink those massive copper cables down to a manageable size, and we highly optimize the spatial footprint of the facility. It is a total paradigm shift for the whole industry. To really wrap our heads around the sheer scale of an AI factory, we have to follow an electron step by step through 4 distinct stages. We start out at stage 1, moving massive power across macro distances on the grid, then into stage 2, stepping it down inside the facility, then over to stage 3, injecting that 800-volt DC power directly into the server rack, and finally, stage 4, the microscopic last-mile conversion right at the GPU core itself. Let's actually walk through this incredible engineering funnel. So stage 1 starts all the way out at the macro level with the external grid. The surging demand for AI is requiring the electrical footprint of a small city just to feed a single cluster. High voltage transmission is the absolute prerequisite here. We're talking about colossal 765 kilovolt transmission infrastructure and ultra-high voltage transformers. Companies like HD Hyundai Electric and Hyosine Heavy Industries are locking in long-term contracts just to build these massive energy highways. This is the heaviest of heavy iron, and right now it is the ultimate pace setter for AI deployment. Okay, moving inside the building for stage 2, power is stepped down at an industrial scale. And what's really fascinating here is the transition from analog to digital control. Global energy giants are actively ripping out heavy, bulky, traditional copper coil transformers and replacing them with these sleek, instantaneously responsive, solid-state transformers. By using power semiconductors instead of massive blocks of iron and copper, these facilities save incredible amounts of physical space and gain the hyper-precise voltage control they absolutely need to protect billion-dollar GPU clusters. Zooming in even further to stage 3, we reach the server rack itself. This is where that 800-volt power is delivered directly to the compute nodes. Instead of huge tangles of wire everywhere, they use continuous copper bus bars to deliver high voltage straight down the cabinet. This minimizes the bulk and completely eliminates transmission heat inside the server environment. This is exactly where specialized power supply units from companies like Delta and Lite-On become incredibly critical, just to safely interface with this massive influx of localized energy. And finally, stage 4, the last mile. Obviously, hitting a GPU with 800 volts would instantly vaporize it, right? So it has to be aggressively and super efficiently stepped down in stages. Relying on advanced gallium nitride and silicon carbide semiconductors, we are literally witnessing a materials science miracle. Over the span of just a few inches, that raging 800-volt industrial power feed is stepped down to an ultra-precise, delicate supply of less than 1 volt, injected directly into the processor core. It is the absolute bleeding edge of power circuitry. Now, you might be asking yourself, why go through all this trouble? Why push the absolute limits of materials science for this hyper-efficient step-down process? Well, it all comes down to one number, 1%. At this immense gigawatt scale, clawing back a mere 1% efficiency premium at the micro level translates to just massive savings. That single percentage point saves millions in operational expenses and drastically shrinks the required cooling infrastructure. When you're dealing with megawatt-class racks, power efficiency is directly proportional to compute density. But of course, taming this 800-volt beast comes with some really severe, potentially catastrophic risks. Because unlike traditional alternating current, which naturally drops to 0 volts periodically, allowing regular breakers to easily interrupt the flow, direct current never drops to 0. It flows continuously in one direction. And what that means is any disconnection, even a slight gap, creates a sustained, lethal bolt of lightning, an electrical arc that literally burns through the air and melts surrounding equipment. Definitely not what you want happening anywhere near a billion-dollar computer. Which leads to a pretty terrifying question for the engineers when it comes to routine maintenance on live multi-million-dollar equipment. In a legacy data center, maintenance is routine, right? You just pull a server out, swap it, done. But how on earth do you hot swap a live server when unplugging it creates a self-sustaining arc of lightning? It requires an entirely new paradigm in electrical isolation. The answer? Well, engineers had to merge the facility power and the IT infrastructure into a single, highly responsive nervous system. They do this by using ultra-fast solid-state breakers. These things replace those old sluggish mechanical breakers, using precision silicon to detect faults and literally cut the circuit in nanoseconds. It extinguishes the DC arc before it even has a chance to form, guaranteeing absolute protection for these trillion-dollar AI clusters. Now, all of this physical reality dictates a really harsh economic timeline. AI models, they iterate at lightning speed, we're talking weeks. Even getting GPUs through the supply chain operates on maybe a 3 to 6 month delay. But those massive, heavy electrical transformers required to actually power the facilities, we are looking at backlogs stretching from 36 to over 48 months. So the actual expansion of AI is moving strictly at the agonizingly slow speed of heavy iron. Operating this whole ecosystem requires a perfect global handshake across a brand new value chain. Down at the micro level, you have specialized power semiconductor engineers from places like Texas Instruments and Infineon handling that sub-1 volt silicon magic. In the middle, integration giants like Siemens and Schneider control the facility. And way up at the macro level, it relies heavily on heavy electrical engineering titans to build out the external grid. It's a completely globally synchronized effort just to turn the servers on. And interestingly, Korean heavy industry is in a really unique position right now to capture massive value at the very front end of this global supply chain. You've got companies like LS Electric with their vacuum circuit breakers, HD Hyundai scaling ultra-high voltage transformers, and Hyosung securing the 765 kilovolt transmission infrastructure. They're out there building the foundational energy highways that have to be physically poured in concrete and erected years before the very first AI chips even arrive on site. So what's the big takeaway here? The ultimate winner in the AI race won't just be whoever designs the smartest logic chip. It's going to be whoever can successfully engineer, permit, and power the most efficient, overarching AI facility. The fundamental vocabulary of AI has permanently expanded. It's not just CUDA, high bandwidth memory, and NVLink anymore. Now we have to talk about power transformers, medium voltage switchgears, 800-volt busbars, and gallium nitride semiconductors. To wrap up this explainer, I want to leave you with a final thought about this completely new strategic moat. We spend all our time obsessing over who commands the silicon, but our future pace of innovation is completely bottlenecked by who commands the steel and the copper. We all know who designs the smartest chips, but the true pacing item for the next decade of human technological advancement will be dictated by who can actually plug them in. It's a completely new battleground, and honestly, the race for heavy iron has only just begun.